This next series of examples takes the same region R, the region enclosed by y equals x and y equals x squared, and it just rotates that same region over different axes of revolution. And this will give us a nice chance to really solidify our understandings of this concept of the washer method. So always start with a graph of the 2D, so y equals x squared, intersects y equals x at the point 1 comma 1, because 1 squared equals 1. And we're going to revolve that around the x-axis. So we'll take this region, this yellow region, this little sliver, and we'll rotate that about the x-axis. So our AR is the x-axis. So notice that the axis of revolution is not a line of our boundary. I don't think that it will be for any of these, because our diagonal line is, that would be a very different sort of thing if we had a diagonal axis of revolution that we won't see. But since our axis of revolution is not a line that coincides with a boundary of our shaded region, then that means that we must have a washer method. There's a gap between the region and the axis of revolution. That gap is the hole in our washer. So we've got ourselves the big R, which is from the axis of revolution all the way to the farthest edge. Notice that we're still making these perpendicular to the axis of revolution. And we've got our little r. All right, so big R, top minus bottom. Big R as a function of x. The top is x. The bottom is 0. Y equals x minus y equals 0. So big R is equal to x. Little r, top is x squared. Bottom is 0. So we've got x squared. So the setup here, the volume for this problem is pi times, don't forget the pi, it's always pi r squared. We're going from x equals 0 to x equals 1, so from 0 to 1, of big R squared minus little r squared. X squared is x to the 4th. All right, so I'm going to go through and I'm just going to set up each one of these. Maybe we'll have some time to evaluate some of them. The setup is the bigger piece of this. So let's make sure we get the setup for as many of these as we can. So same region. This time the line of revolution is y equals 2. So let's keep that in orange. Let's stay consistent here. The AOR is y equals 2. Okay, so again, this shaded region does not lie right up against the axis of revolution. There's a gap in between them. So that means that it's a washer method. Again, so from the axis of revolution, we're going to go all the way down to the farthest side of the shaded region. That's my big R value. My little r value is going to start at the axis of revolution and go all the way down to the beginning of the shaded region. So we've got our two r's. Big R is found top minus bottom. This time the top is 2. Let's make sure that we remember that this is a function of x. So r of x equals, let's see, we have 2 minus, that's the top, the bottom is y equals x squared. So 2 minus x squared is big R. For the little r, we're starting at the top again, so that's little r is 2 minus, this time we stop when we get to here, and that's at y equals x. So this volume is going to be, oh, I forgot the pi after saying don't forget the pi. Pi integral still from 0 to 1 of big R squared is 2 minus x squared squared minus little r squared. That's 2 minus x squared. So that you can see is going to be a more involved antiderivative because we've got to square these out, perhaps combine some like terms, but it's going to be a little bit more complicated than this one. But again, the setup is what I'm focusing on right now. Changing it up so that we've got this axis of revolution that's down below at y equals -5, same shape, right? Y equals x squared, y equals x. This time we're going to be way down here at y equals -5, perhaps not drawn to scale. It's all relative though, right? It's down below, which is what we care about. Y equals -5. So when we take our shaded region and we revolve it around this axis of symmetry, notice that the big R value starts at the axis of revolution. All the radii are always measured from the axis of revolution. And this one goes until we get to the far edge of the shaded region. Notice that the far edge could be the curve, like it is over here, or it could be the line, as it is over here. It just depends on where your axis of revolution is. So big R is there, whereas little r is there. So big R of x is top minus bottom, so that's going to be x minus -5. And little r of x is going to be x squared minus -5. So our volume is going to be pi times, once again, the integral from 0 to 1 of x minus -5 is x plus 5. We'll square big R. And then we'll also square little r. We'll subtract those two values. So x squared plus 5 quantity squared is the little r squared. And then we will subtract big R squared minus little r squared and get that dx out there as well. And that would be a good setup for for that problem. If you happen to get the big R and the little r mixed up, by the way, then the only problem is that your answer is going to end up being negative. So if you get a negative answer, check to see if you got your big R and your little r mixed up. At any rate, all of these had a horizontal axis of revolution. Take a look at these. The y-axis, x equals -1, x equals 17. All of these are going to have a vertical axis of revolution. So that means that when we draw our rectangles that are perpendicular to the axis of revolution, those rectangles are going to be horizontal. So everything that was in terms of x, we're now going to do them in terms of y. So that's definitely something we want to keep track of. So instead of saying this is the curve y equals x squared, I'm going to say this is the curve x equals the square root of y. And there's nothing we have to do about y equals x, right? Because y equals x is the same thing as x equals y. So that part doesn't matter. So that's still the same shaded region. This time our axis of revolution is vertical. The AOR is x equals 0. So always measure a radius from the axis of revolution. The big R is going to go through the shaded region to the far side, which is a great comic strip, The Far Side. It's also a good rap group, isn't it? So many things that are great about The Far Side. So anyway, this is my big R value. And then my little r value is going to be from the axis of revolution to the near side. Oh, the dark side of the moon, that's another good thing, right? Dark side and far side are not the same thing, though, are they? Anyway, big R, this time we're finding radius in terms of y. It is an x value. It's a horizontal distance that we're measuring in terms of y. So instead of top minus bottom, for all of these, we're going to do right minus left. So the right side of the big radius is the square root of y. And the left side of the big radius is x equals 0. Little r of y is the y value, or the x value, which equals y, so y minus 0. Okay, so pretty much the same idea, except make sure that we have a dy instead of a dx. On this particular problem, it's impossible to mess up the bounds, because whether we're talking about going from x equals 0 to x equals 1, or y equals 0 to y equals 1, it's always going to be from 0 to 1. R squared is y, and other r squared is y squared. Big R squared is y, little r squared is y squared. So that would be the setup for that one. That would be probably, I guess, the easiest of any of these integrals to do. All right, so moving on to the next one. This time we've got x equals -1, so that's going to move off to the left. So we've got the same shaded region. This time we've got our axis of revolution over here. AOR. The AOR is x equals -1 this time. We're still taking that same old region every single time. We're using the same region and finding big R and little r, measuring from the axis of revolution. So going way over to here, we got our big R value. That's big R. Well, point to that. That would be the dy if we're pointing to that side. That is big R. And then if we go to the near side, that would be little r. So big R is a function of y. These are x values. The right side would be the square root of y again. Right minus left. So right minus left is going to be right minus -1. And then little r, same deal. This time it's going to be not root y, but just y, because that's the line, minus -1. Okay, so the volume equals pi times the integral from 0 to 1 of big R squared is root y plus 1. We're subtracting a -1. So, and then little minus little r squared, that's going to be -1 plus y plus 1 squared. And that would be a bit of a pain to deal with, but certainly something we know how to do, right? We can square this, we can square this, we can subtract, reduce, combine like terms, all that jazz, and we can evaluate this. And then finally, our last example, we'll have x equals 17. So that's going to go way out there. So if we put x equals 17 way out here, AOR is x equals 17. Then we've got this yellow shaded region. Big R goes from the axis of revolution all the way to the far side. That line this time is the far side. So that's big R. Little r is going to stop at the near side, which is the curve this time. So big R, right minus, whoops, this is a function of y. Big R of y is the right side, which is 17, is the x value. The right side is y. Y is the x value, and that's big R. Little r of y is right minus left, so 17 minus the square root of y. So our volume in this problem would be pi times the integral from 0 to 1 of big R squared minus little r squared. Now the next step will be to evaluate each one of these. I'll leave that as an exercise for you. Remember that you can check these in a calculator as well. So after you've evaluated it by hand and gotten an exact answer, use your calculator to give yourself a little self-check and see how you did.